C. We are proving more circle conjectures today, but actually only one conjecture, right? So that's good. We are proving the inscribed angle conjecture, which we introduced yesterday. It states the measure of an inscribed angle is half the measure of its intercepted arc. This conjecture is unique to any other conjecture we've done so far. We've learned that to prove something to be true, we must prove it to be true for all possible scenarios. Up until now, any single conjecture we proved to be true, we had to produce one proof. But the inscribed angle conjecture is a little bit different. In order to prove it is true, we have to prove it for all possible inscribed angles. But there are an infinite number of inscribed angles. But every inscribed angle falls into one of three cases, and that's what we're seeing here. The first possible case is that the inscribed angle has the center of the circle on it. The second possible case is that the circle's center lies outside of the inscribed angle. And the third possible case is that the center circle lies inside of the inscribed angle. So unfortunately, in order to prove the inscribed angle conjecture, we have to produce three proofs. We have to prove it is true for each of the three cases of inscribed angles. When we learn proofs, we learn to build an argument before we start to write the proof. We're going to use this circle with the inscribed angle going through the center of the circle to build our argument. In order to prove case one of the inscribed angle conjecture, we have to draw in that radius. Now I'm going to go ahead and call this inscribed angle ABC of circle O. And I've drawn in radius AO. Let's also label our inscribed angle as a measure of x. We're going to call this angle as a measure of y, and the central angle AOC as a measure of z. Keep in mind that those lowercase letters represent the measures of the angles. They're not the actual angles. Right? So we can't call it angle x. It's angle ABC. So in our brainstorming, we are noticing that Z is an exterior angle to triangle ABO. And we know the exterior angle theorem says that an exterior angle equals the sum of the two remote interior angles. So we're going to have Z equals x plus y. Now, we're not actually writing the proof yet, we're just sort of jotting down notes. We also know that by the definition of arc measure, the measure of the central angle, which in this case is Z, would be equal to the measure of the arc, of its intersecting arc, which in this case is arc AC. So maybe those play into the proof, we have to keep brainstorming. BO and AO are both radii, so we know that they are congruent, right? So BO congruent to AO, and we can even mark that here on the diagram. So now we know that triangle BOA is isosceles. And that means the base angles are congruent, which means x would equal y, since x and y represent the measures of those base angles. So since z equals x plus y, and x equals y, we can substitute x for y and have z equals x plus x. Then, with simple algebra, that means z would equal 2x by combining our like terms. And then divide both sides by 2, and we get z over 2 equals x. Or in a sense, x equals half of z. And since z equals the measure of arc AC, we'd end up with x equaling half the measure of arc AC. We just built our proof right there. But now we have to write it, which, as we've talked, is a whole other skill. Let's start with the given information here. We are being given circle O with angle ABC inscribed. We need to prove that the measure of angle ABC equals half the measure of its intercepted arc, which is arc AC. We're going to use a flowchart format. Okay, yesterday's proofs we did 2 columns, today we'll do a flowchart. So we're going to start out with BO congruent to AO. And we know that that's true because radii of a circle are congruent. Since BO is congruent to AO, we know that triangle BOA is isosceles. Definition of isosceles triangle. Since triangle BOA is isosceles, we know that the base angles are congruent, which means their measures are equal. X equals y, isosceles triangle theorem. Coming into the proof on its own, no arrows leading to it. We know that Z is equal to x plus y by the exterior angle theorem. So now we're going to take this box and this box. And we're going to say Z equals 2x. I'm actually doing 2 things here in one step. I'm substituting x for y, so that's substitution. And I'm combining like terms. You definitely could represent these as 2 separate steps. I'm just trying to be as efficient as possible. So I put them into one step with 2 justifications. So we now take our equation here. We divide both sides by 2, so we get x equals 1/2 Z. That's the division property of equality. Alright, so now we're pretty much done with the proof. We've shown what we want to show, but now let's sort of clean things up. We know that x is equal to, in our diagram, the measure of angle ABC. And that really is just given information based on how we set up our diagram. And we know that Z is equal to the measure of arc AC. That is by the definition of arc measure. Let's see. And so now we can bring all three of these together, here, here, and here, to say the measure of angle ABC, I'm going to have to move this, is equal to 1/2 the measure of arc AC. By substitution. And now we've proven case 1 of the inscribed angles conjecture.